I'm Omer Levy. I'm a research scientist at Facebook AI Research. I do a lot of things in NLP, but I'm mainly known for breaking models, getting negative results, and that kind of stuff. And currently, I'm actually more interested in getting maybe positive results, and that's what I hope to discuss today on the show.
To kick things off a little more, can you tell me a little bit about your academic background and especially your interest in NLP?
Yeah, so I did my PhD at Bar-Ilan University, followed by a postdoc at UW. My PhD I did with Ido Dagan and Yoav Goldberg, and a postdoc with Luke Zettelmoyer. Yeah, I've been kind of in the field for, I think, 7 years now. Not that young, but not that old either.
Definitely. So on the show, we've been talking about BERT. Not every episode has come out, but I'll take for granted that listeners at least should by now know what BERT is. So I'll skip that question and just ask you if you could put it into context, maybe some way in which you've been applying it.
BERT has had an incredible effect on the NLP community. I think that's pretty obvious by now. In one sense, and this has also affected me personally, BERT kind of killed a lot of projects that were trying to create or design a model that is specific to a certain task. BERT came along, this kind of massive, pre-trained mass language model that within 3 training epochs on the target task, it's getting state-of-the-art results and putting all those handcrafted models, leaving them way behind.
A lot of people's first impression of BERT is to be impressed with it. What was your journey towards questioning where its boundaries lie?
In SpanBERT, we're not per se trying to understand what the limits of BERT are, but that is still a really, really interesting question. I have had other work that tries to kind of analyze what BERT learns. We actually just got a Best Paper Award in the Black Box NLP workshop for that paper. That's work with Kevin Clark, Urvashi Khandelwal, and Chris Manning. And other people have written similar papers and basically found out that BERT is kind of learning the whole traditional NLP pipeline in some implicit manner and it's getting a lot of gains from that. But I don't think that we have seen kind of what the limits of BERT or BERT-like models are at this point.
Can you tell me a bit about how SpanBERT, which is, I guess, the shortest way to describe your contributions, what's the long way? What are you guys innovating on in your research?
So in SpanBERT, what we tried to do is improve the pre-training tasks that BERT is using. BERT is not a model, but a pre-training method. In that pre-training method, BERT has 2 objectives. One is the masked language model. The other is text sentence prediction. We focused on mainly improving the masked language model. So the masked language model itself, the way it works is that you get a sentence, say, I had a nice chat with Kyle, and then you randomly pick some of these words, mask them, let's say we mask chat, and the model needs to predict the missing word in I had a something with Kyle is chat. To make that harder, kind of to force the model to capture more interesting things about language. And I'm keeping this vague intentionally. We'll go into that in a second. What we did was first, instead of masking random tokens, we masked random spans of tokens. So now we're not saying, we're not giving the model as input, I had a nice something with Kyle. We're saying, I something with Kyle. And that gives it a bit more flexibility in the things that it could potentially predict. But by making the task more challenging, we're basically forcing the model to learn more about language. The other thing we added was that we're not only forcing it to predict these missing words, this missing span from each of the individual masked tokens, but we're forcing it to predict this information from the boundaries of the masked span. So from the word I and with Kyle, we're trying to predict everything that was in between.
Tell me more about that limit. Does that mean I'm not going to consider things like the length of the span?
We didn't change the length of the sequence. So the model knows what length it's trying to predict, but it needs to kind of, I'm saying this in a bit of a hand-wavy way, it needs to learn longer range dependencies. So it needs to learn not only what the kind of immediately neighboring words are going to be, but what the next 3 words are going to be, or 4 words, depending on the length of the span.
The idea is novel and appeals to me, and I think you put it pretty succinctly when you said we want to force the model or the learning process to learn more effectively. But as I also think about it, I wonder, well, okay, you've made the problem harder. If you train your model with your method on the exact same training data set, we hope that that effort does in fact force the model to be smarter. Do you have any way to quantify the degree to which that's true?
So that's a great question. And we actually put a lot of effort and especially time and resources into making sure that we're giving Bert a real fighting chance, the original Bert, a fighting chance to beat us. In addition to taking Google's version of Bert and just download, whatever they made publicly available, we also re-implemented Bert ourselves, and we did a bit of hyperparameter tuning, and every kind of training trick, be it data or hyperparameters or training for more iterations, stuff like that, we also applied to the Bert baseline. So we had baselines that were actually much, much stronger than the original Bert, and we were still able to outperform them when we added the SpanBERT objectives and pre-training tasks.
Very neat. And is there any way you can measure that, or is it more qualitative as you introspect the results?
If you allow me to go on a bit of a tangent here.
Please.
This is a question we've been asking since 2016 when, along with Felix Hill, we ran the Rep Eval workshop. This was in ACL 2016. Since then, Sam Bowman joined us and actually kind of took the lead on this. We came together to make this shared task that everybody's been running on, Glue. I think most of our listeners have heard of it. And now we have also Super Glue, which is kind of the next generation, much harder tasks as well. Glue is a really, really good way, or was a good way until it kind of got maxed out by all these models. But it's a really good way of evaluating how well these pre-training tasks are actually working, because it evaluates a diverse set of tasks with different types of, training set sizes, different levels of complexity, of difficulty. If you manage to improve the results on Glue by, say, 2 points, that's really, really meaningful. I'll mention another work that we did kind of concurrently. It started actually from kind of the same parent project, but split off into two things. One of them was SpanBERT and the other being Roberta. So Roberta, the idea was basically, let's try to replicate BERT, but do a lot of hyperparameter tuning and scaling up that the original BERT just didn't do because, I don't know, they thought it was big enough and good enough, which it really was at the time. But apparently what we found in Roberta was that you can do a little bit of tweaking to the hyperparameters. So for example, just training it for a bit longer, maybe training it with bigger batch sizes, using a different kind of VPE, adding more data, and it just works really, really, really well. In fact, it works so well that on Glue, for example, we were able to outperform XLNet by a little bit. So it's kind of
That's really saying something.
yeah, I would say within variance, but basically, without adding all those modifications that XLNet added to the model. So we just, we basically had the simple BERT model. We even simplified it even more. We removed the next sentence prediction, the NSP objective. We did in SpanBERT as well, and used just a single sequence to train each example, and just scaling it up, training it for longer, using slightly better vocabularies, just really, really improved performance on a bunch of tasks. So not only Glue, we also just released results on Super Glue as well, where there's a really, really big leap. It's not at human level yet because Super Glue is significantly harder. It has a bunch of tasks that are significantly harder than the ones that we have in Glue, but still, it's a huge advance in Super Glue.
Yeah, absolutely. I seem to recall from the paper on a lot of tasks like putting your approach to the challenge with the famous Squad and Squad 2.0 data sets, that you were eking out those valuable percentage points improvements on SpanBERT when compared to vanilla Google BERT and a few others. I know all deep learning is a little bit inherently black box, but do you have a sense of the mechanism or what it is that is allowing your model to outperform?
I think really the most impressive results were in what we call span selection tasks. So squad 2, a lot of the machine reading, question answering, shared task data sets that we ran on, we see this really significant improvement there. This is probably because SpanBERT is focused on representing and predicting the content of missing spans. And I think that's why we're getting gains on these. I'll also mention one other task that we ran on, which most people don't run on because it's a bit more complicated, which is coreference resolution. Coreference resolution is a really hard task for models. Currently, we have the state of the art on this. It's about 79 F1, whereas before us, the best model was from Kenton Lee and others, which was about 73, if I'm not mistaken, F1. So there's a really big jump there. A lot of the jump is coming from just using BERT, but we can also outperform BERT on that by adding the whole span-based pre-training and objectives.
Today, 43% of college grads work underpaying jobs that don't require a degree, while 200,000 tech jobs go unfilled in high-growth industries across the U.S., according to research by Burning Gas Technologies and Strata Education Network. Flatiron School can give you the skills to build a career you love. At Flatiron School, you'll learn data science from seasoned instructors and study a carefully structured curriculum designed to introduce you to the math, programming, algorithms, and data engineering skills to prepare you for a career as a professional data scientist. Your education will be paired with career support from our best-in-class career services. You'll meet weekly with a dedicated career coach on resume review, interview prep, and build an employer network to help you land the job you want. Complete details are available at flatironschool.com/terms. Learn more at flatironschool.com/dataskeptic.
And I know you guys went to great lengths in a similar manner that the initial BERT paper tried to make a fair comparison to Elmo, which was sort of its benchmark. You made a fair comparison to BERT, or at least you certainly worked hard to do that. Can you tell me what you consider in that apples-to-apples comparison? Is it compute time or cost or iterations? How do you measure the training experience, I guess, between the two approaches?
We tried to stick as much as possible to the original BERT. In addition to just downloading whatever Google made publicly available, we had our own re-implementation of BERT, which we ran with exactly the same corpus that we used to pre-train SpanBERT. And every time we tried a different hyperparameter for SpanBERT, we also ran that option for BERT and took the best one.
Is that a hyperparameter that was very effective when you tuned it, or what sort of results did you see as you played around there?
Yeah, so one of the interesting findings we had when we tried to come up kind of with, the best benchmark was what happens if you remove the next sentence prediction task that BERT had. And here we found that if you remove it, and actually I'll maybe be a bit more accurate, it's not only about removing the objective, but also removing the fact that you sample two sequences. Instead of sampling two sequences like BERT does, and then trying to predict whether one sequence is the continuation of the other, we're just sampling a single sequence at each time. And that single sequence is actually going to be longer because instead of having like two sequences of, say, 256 tokens, you suddenly have one long sequence of 512 tokens. So the model has the potential to learn much longer dependencies as well. So doing that both to our model and to BERT, to the original BERT, actually improves performance quite a bit. There are a few cases where you see a bit of a drop, but really, in most of the tasks we did, especially in the major tasks like multi-NLI and squad, you actually see quite a big of an improvement from removing the whole by-sequence training approach and just going towards single sequence training.
And I think we've sort of covered this, but I want to ask just to make sure I understand it explicitly. That masking procedure, is that a fixed width mask or is it dynamic in some way?
We played around with a bit of masking schemes, although admittedly it's kind of a rabbit hole. You can always try other ways to mask spans. What we eventually came up with was this kind of geometric distribution for deciding the length of the span. So we basically randomly sample the length of the span from a geometric distribution. So it means that you're most likely to get a length of 1 or 2, but with some probability you might sample a span of length 10, for example. Each time we sample the length of the span, mask it, and sample the length again for the next span until we run out of our budget.
Like you said, I don't think there's a way to derive from first principles what that distribution should be. But could you talk a little bit about the decision to arrive at that geometric distribution and not say have all 7, 8, 9 length sequences or something like that?
It was kind of an empirical decision at the end of the day. We tried a bit of other things, of random masking schemes as well at the beginning, and this looked both elegant on one hand, worked well on the other hand. I'm not sure that there would be a significant difference if you use some other distribution as long as you're sampling different lengths.
Yeah, that makes sense.
If you just sample length 2 or length 3, I think you're missing out on these longer spans that kind of make it more interesting or more challenging for the model. We also tried to mask spans that are kind of linguistically motivated. So for example, what if we masked out random noun phrases or random named entities? It turns out that the differences are rather small, and if there are any, they're usually in favor of just randomly sampling the spans. And this is actually a really... We were really happy about this result because it means that, you could run this model on languages, for example, that don't have named entity recognizers or constituency parsers that operate at, with enough accuracy.
One of the areas in which SpanBERT has good success is on natural language question answering. For starters, can you tell me why is that a hard problem?
I'm not sure it's a hard problem anymore, given the results we have. No, I'm of course being a bit cynical here. So the benchmarks that we have were challenging until, say, a year ago, at least in this field. Bert has kind of destroyed some of the... No, I wouldn't say destroyed. Let's say Bert has really kind of approached the human level performance of these benchmarks. It's a good question why. One hypothesis is that the way these benchmarks were created were by basically going to Mechanical Turk and asking people to write questions based on the answers or based on a given text. And when you ask people to do that process, especially when you go to Mechanical Turk to do it, you don't necessarily get a very natural distribution of questions. You might be getting an easy distribution of questions.
Yeah.
And it could be that that's the reason that these tasks are maybe less challenging for something like BERT. One of the pieces of evidence we see that kind of supports this hypothesis is the natural questions dataset from Google. That's proven to be really, really challenging for BERT. I think it's also much more challenging for humans. So it's not only a BERT-only phenomena or a model-only phenomenon. We specifically didn't really run on the original natural questions dataset. We ran on kind of a derivation of that. It would be really interesting to see how models like SpanBERT are improving on natural questions and whether there still is a big gap between model performance and human performance there.
One of the things about BERT that certainly captured my attention was the way in which it performed and even set the benchmark at the time on a variety of tasks that to me were unrelated. And SpanBERT has continued that tradition and kind of breaking some benchmarks across the board. From your empirical results, is there anything that SpanBERT seemed to excel at? In other words, does the span method assist in certain types of problems more than others, or is it just sort of a general lifting of all ships?
Our original hypothesis was that it would benefit mainly span selection tasks, like extractive question answering, squad, for example. Coreference resolution is another case where we're doing basically reasoning over spans. It turns out that it indeed does help these tasks quite a lot. But in addition, we also saw gains on general tasks like glue, for example. So I would assume that in general it helps the performance. You can't say... It's a bit hard to make these claims,
Sure,
in general, because there's only a finite amount of benchmarks you can run. But it seems to be that the improvement is rather across the board, particularly substantial when it comes to span selection tasks.
Did you need to take any precautions to ensure that span-based methods didn't overfit in some way?
So we took the same precautions that the regular BERT took. We basically did a bit of dropout. But also, I should mention that when you train a model on this amount of data, it's a bit harder to overfit. I'm not saying it's impossible, but a lot of data is just a really good regularizer. We don't need to worry about that too much. When we did fine tuning, there was a bit of an overfitting issue in some of the smaller data sets, and there we just fine tuned on less steps, and that seemed to make the problem go away.
And then appealing to what you said earlier about your history of breaking models, knowing the sort of landscape of different BERT-like models, what do you think are the most effective techniques for fooling them today?
I think you can always find kind of a gotcha example where these models will fail and look really, really stupid. But it's getting harder and harder to find a systematic way of doing that. We're going to find these examples for a long time, and we're hopefully going to find systematic ways to break them for a long time. But it is getting harder. I think like 5 years ago, or even 3 years ago, when we had LSTM-based models that were much, much smaller with no pre-training, you could see it pretty easily. We had a paper, for example, called Zero-Shot Relation Extraction via question answering, via reading comprehension, I think, where we showed that if you train a question answering model, which was at the time a state of the art on Squad, if you train it on a bunch of questions that appeal to like one topic and then ask it a question on a completely different topic, it just won't know what to do. It'll fail pretty miserably, and even in cases where the answer is verbatim in the text, it will fail to find it. So I think the pre-training kind of alleviates a lot of these very simple tricks that break the model, but I don't know, maybe we just haven't found newer tricks to to break the models, and this is definitely an area of research that really, really interests me.
Yeah, me too. I'm very excited to continue to follow it. With that in mind, what's next on your research agenda? Or maybe your implementation agenda, which is another path as well?
It's really, really competitive to work on these BERT-style models, or BERT-scale models as well. It's something that I feel like, I'm currently at FAIR, so we have the privilege of working on this and scaling up to an insane amount of computational resources. But one thing that I would really like to do is to find a way to scale down the models to democratize this field and basically have universities and startups and other institutions that don't have this kind of level of resources join the game and compete in finding better ways to train these models.
Yeah, that's true. I mean, even though like Google's version of BERT is open source, and I use it in my production system, we run 4 very large machines because it's so memory intensive. So it's cost prohibitive even for a small POC of it. So I think that would be an excellent breakthrough to find ways to reduce these models.
I think it's also going to be really, really hard. Like I've been thinking about this for some time now, and it kind of looks like just adding more data, adding more compute is kind of the straightforward but effective way.
Yeah, it's working right now.
Exactly, just getting better performance. Being efficient is hard. Like we've had some experience on trying this, and I haven't been able to do anything like, scale it down by 10x or something while preserving performance. It's really, really challenging.
Omer, thanks again for coming on the show. Is there any way people can follow you online?
First of all, thank you so much for inviting me. This has been a real pleasure chatting with you. Everybody's welcome to email me. I don't tweet that much, but you can also follow me on Twitter. That's at Omer Levy _. Yeah, that's more or less it.